In this video, we will learn the concept of change of variable, specifically focusing on how to apply it and when to use it. We will start by looking at the process step by step. Suppose we have the function that is depending upon two variables x and y. Further, these x and y variables are depending upon two variables u and v. In previous videos, we learned how to compute the derivative of function with respect to u, that is a partial derivative, and partial derivative of a function with respect to v using a chain rule. In that case, we were able to express these derivatives in terms of partial derivative of function with respect to x and partial derivative of function with respect to y. Now suppose we need to compute partial derivative of function with respect to x and partial derivative of function with respect to y, but in terms of partial derivative of function with respect to u or partial derivative of function with respect to y. In other words, we want to express the derivative with respect to x, y, but by using u and v as an independent variable. This is where the concept of change of variable becomes useful. We can derive this new set of derivative by using a chain rule. According to the chain rule, if you want to calculate the partial derivative of function with respect to u or v, we can express them by using these two formulas. That is partial derivative of function with respect to x into partial derivative of x with respect to u plus partial derivative of function with respect to y into y with respect to u. When we need to take the partial derivative of function with respect to v, we replace u by v. As you can observe, our requirement is what is the value of partial derivative of function with respect to x and partial derivative of function with respect to y in terms of these two derivatives. Same form is available in a second equation. To find the value of partial derivative of function with respect to x and y, we treat the system of partial derivatives as a system of equation. We can write this as a1x plus b1y is equal to c1, a2x plus b2y is equal to c2, where a1 represents the partial derivative of x with respect to u and x, that is unknown, that is partial derivative of function with respect to x, plus partial derivative of y with respect to u, that is the value of b1. Y is replaced by partial derivative of function with respect to y, that is the unknown, is equal to known quantity is partial derivative of function with respect to u. Same format we can construct for the second equation. Our goal is to find the values of partial derivative of function with respect to x and y. For that, if you want to find the value of x and y in this case, we can use Cramer rules. According to the Cramer's rule, we can find the values of unknown x and y by this form. Same Cramer rules we can apply on this equations. In term of x, we have partial derivative of function with respect to x. At the place of y, we have partial derivative with respect to y, and this one is as it is. C1, C2 are replaced by partial derivative of function with respect to u and v. B1, B2 are replaced by partial derivative of y with respect to u and v. And A1, A2 are replaced by partial derivative of x with respect to u and v. Further, we can use one more result, as we know that determinant of A is equal to the determinant of A transpose. We can write this in this form where we have taken the determinant of each matrix. There is a specific name for this one. This term is written as partial of function and y divided by partial of uv. It means it is a determinant where we are taking the partial derivatives of function derivative with respect to u and v in a first row, and in a second row derivative of y with respect to u and v. Similarly, we can write this as partial derivative of function with respect to y, and this determinant written as partial of x and f, that is the derivatives of x and f, by u and v, that is a partial of u and v. This is equal to 1 by here partial of x and y divided by partial of u and v. Moreover, we have more simplified form of this, that is a partial of xy divided by partial of uv. This is called as a Jacobian of the variable of transformation. In our scenario, we have considered a function that is depending upon x and y, and further they are depending upon u and v. When we are taking the partial derivative of x and y with respect to uv in a matrices formed by this, that is called as a Jacobian. From here, we have the partial derivative of function that is equal to 1 by this term that can be represented by j as a Jacobian into this, that is a partial derivative of function comma y divided by partial of uv. Similarly, we can write the partial derivative of y, that is equal to 1 by j partial of x f divided by partial of uv. This is also written as 1 by j. If you switch these two values, x as a f as a x, we will get a negative sign outside, because when you swap these two variables, it means we are swapping two rows. Rather than taking a partial derivative of x with respect to u and v in a first column, we are taking the derivative, that is partial derivative of function with respect to u and v. It means we have interchanged the two rows, and with the interchange of two rows, getting a negative of the same determinant. In conclusion, whenever we have a function that is depending upon two variable x and y, and further they are just depending upon two variable u and v, first step in a change of variable, we will calculate the Jacobian, that is a partial of xy divided by partial of uv, and that is the basically a determinant. Partial derivative of x with respect to u, then x with respect to v, partial derivative of y with respect to u, y with respect to v, and partial derivative of function with respect to x in terms of uv is calculated as 1 by j into the similar term, but in terms of x we replace f and the rest of the terms are as it is. And that is again a determinant of the partial derivative of f with respect to uv in a first row, then derivative of y with respect to uv in a second row. Similarly, we have the partial derivative of function that is equal to 1 by j. Use the same expression, but in place of y replace f. In case we have the function that is depending upon three variable x, y, z, and they are further depending upon u, v, w. Now, how to calculate the partial derivative of function with respect to x, y, z in terms of u, v, w? What we can do, very first step, we will calculate the Jacobian. Jacobian is equal to partial of x, y, z divided by partial of u, v, w. That is equal to determinant. Here we will calculate the derivative of x with respect to u, that is a partial, as it is depending upon more than one variable. Partial derivative of x with respect to v, partial derivative of x with respect to w. Then partial derivative of y with respect to u, y with respect to v, y with respect to w. Then calculate the partial derivative of z with respect to u, partial derivative of z with respect to v, z with respect to w, and then calculate its determinant, that is the value of Jacobian. And the partial derivative of function with respect to x is equal to 1 by j partial of, in place of x write f, and rest of the variables are as it is. In this case, 1 by j partial of, in place of y write f, and the rest of the variables are as it is. And partial derivative of function with respect to z is equal to 1 by j partial of x, y, and in place of z write f divided by partial of u, v, w. This is how we can construct the formulas for the change of variable if we have a 2 variables or a 3 variables. Here we have taken the example. In this case, we need to show that if the function is depending upon two variables x and y, where x and y are depending upon two variables r and theta, then we need to show this expression, that is partial derivative of function with respect to x whole square plus partial derivative of function with respect to y whole square is equal to this. It means we need to find what is the partial derivative of function with respect to x and with respect to y. Before that, analyze this question. According to this, z is a function of two variables, that is x and y, and z can also be written as a f. Further, x and y are depending upon two variables r and theta. It means we need a derivative of function with respect to x and y in terms of r theta. Means we need to apply the change of variable concept. In that case, we need to find the Jacobian first, that is equal to partial of xy by partial of r theta, that is calculated as determinant partial derivative of x with respect to r, partial derivative of x with respect to theta, y with respect to r, and y with respect to theta. This is further is equal to partial derivative of x with respect to r is what? When we take its derivative with respect to r, theta is constant. Its derivative is cos theta. Partial derivative of x with respect to theta, keeping r as a constant. Derivative of cos theta is minus sin theta. We have minus r sin theta because r is constant. Derivative of y with respect to r, keeping theta as a constant, that is a partial derivative. In this case, that is equal to sin theta. Partial derivative of y with respect to theta, keeping r as a constant, that is r cos of theta. This is equal to r cos square theta negative of negative r sin theta, that is r positive sin square theta. This is equal to r. In this case, the Jacobian value is equal to r. Now we need to calculate the partial derivative of function with respect to x, that is calculated as 1 by j, and in place of x place f, and rest of the variables are same. Similarly, we can write the formula for calculating partial derivative of function with respect to y as 1 by j partial of x, in place of y write f, and the rest of the variables are as it is. Now calculating the first partial derivative of function with respect to x, the value of j is equal to r. This means we need to calculate the partial derivative of function with respect to r, partial derivative of function with respect to theta, partial derivative of y with respect to r, y with respect to theta, and then we need to take its determinant. This is equal to 1 by r. Partial derivative of function with respect to r. As function is not defined explicitly, we take this term as it is. We can write partial derivative of function with respect to r, and here partial derivative of function with respect to theta as it is. Partial derivative of y with respect to r and theta, that we have already calculated in the Jacobian, that is in a second row. This value is equal to sine theta and here r cos theta. Find its determinant, that is equal to 1 by r cos theta, partial derivative of function with respect to r minus sine theta, partial derivative of function with respect to theta. Similarly, calculate partial derivative of function with respect to y, that is equal to 1 by j, that is r, determinant of partial derivative of x with respect to r, x with respect to theta. Then partial derivative of function with respect to r, partial derivative of function with respect to theta. This is equal to 1 by r. Partial derivative of x with respect to r and theta we have already calculated in the Jacobian, that is cos theta and minus r sin theta. Partial derivative of function with respect to r and theta. Function is not defined explicitly. We can write partial derivative of function with respect to r as it is, as well as partial derivative of function with respect to theta as it is. This is equal to 1 by r cos theta into partial derivative of function with respect to theta. Negative negative is a positive. R sin theta into partial derivative of function with respect to r. On left hand side, we need to calculate this one. We need to take their squares. What are the squares of these terms? Its square is 1 by r square. Here we can apply a minus b whole square, that is a square, that is r square cos square theta, partial derivative of function with respect to r square, plus b square, that is a sine square theta, partial derivative of function with respect to theta whole square, negative of 2 into ab, that is r cos theta sine theta, into partial derivative of function with respect to r and theta. Similarly, calculate the square of this term, that is equal to 1 by r square. Square of this term is cos square theta into partial derivative of function with respect to theta whole square plus r square sine square theta into partial derivative of function with respect to r whole square plus twice of r cos theta sine theta into function derivative with respect to theta and r. Now add these two terms. In both the terms we are getting 1 by r square. We can write 1 by r square outside. This is r square cos square theta, partial derivative of function with respect to r whole square plus sine square theta, partial derivative of function with respect to theta whole square, minus we can write 2 cos theta sine theta as a sine 2 theta. We have r sine 2 theta, partial derivative of function with respect to r into partial derivative of function with respect to theta, plus we have taken this term outside. Remaining terms are cos square theta, partial derivative of function with respect to theta whole square, plus r square sine square theta, partial derivative of r whole square, plus 2 cos theta sine theta is a sine 2 theta. We can write r sine 2 theta, partial derivative of function with respect to theta and partial derivative of function with respect to r. Now this term and this term is same, but opposite sign we can cancel it out. Remaining terms are, in this case, what is the coefficient of partial derivative of function with respect to r? The coefficients are r square cos square theta, and the second is r square sine square theta. Here 1 by r square as it is, plus coefficient of partial derivative of function with respect to theta whole square is sine square theta plus cos square theta. Sine square theta plus cos square theta is 1, and here when you take r square outside, we have cos square theta plus sine square theta. This is again 1. We can write 1 by r square into partial derivative of function with respect to r whole square into r square plus partial derivative of function with respect to theta whole square. Simplify this, that is equal to partial derivative of function with respect to r whole square plus 1 by r square partial derivative of function with respect to theta whole square, and that is equal to right hand side term. Based on the Jacobian, we have one more result, that is the variable of transformation, where we have taken u in terms of x, y, z, v in terms of x, y, z, w in terms of x, y, z. These three variables are called functionally related if their Jacobian is equal to 0. When we are saying that u, v, w are depending upon three variable x, y, z, and if we are calculating its Jacobian and it is getting a 0, we say that they are functionally related. Means there exists a relation between the variable u, v and w, and we can say that transformation is not independent. For example, we need to show that the variable u is equal to x minus y plus z, v is equal to x plus y minus z, and w is equal to x square plus xz minus xy are functionally related. For that, in this case, u, v, w are depending upon three variable x, y, z. We can find the Jacobian, that is derivative of u, v, w with respect to x, y, z. That is calculated as determinant partial derivative of u with respect to x, then u with respect to y, then u with respect to z. In the next row, partial derivative of v with respect to x, with respect to y, with respect to z. Then in the next row, partial derivative of w with respect to x, then w with respect to y, then with respect to z. This is equal to its partial derivative with respect to x, means keeping y and z as a constant, that is 1. Its derivative with respect to y, keeping z and x as a constant, minus 1. Partial derivative of u with respect to z means x and y are constant, 1. Similarly, calculate the partial derivative of v with respect to x, y and z. That is equal to 1, 1 minus 1. Derivative of w with respect to x, keeping z and y as a constant, that is 2x plus z minus y. In a second row, partial derivative of this function with respect to y, that is minus x. Next is the partial derivative of w with respect to z, that is equal to x. Take the determinant. When you take its determinant, we will get 0. If the determinant is equal to 0, we can say that the variables are functionally related.